So for free oscillations, we're looking at the scenario where the forcing function is equal to 0. And so first, let's look at free undamped oscillations. So in the undamped case, it looks like mx double prime plus kx equals 0. And if you take a look at this, this has the same general form as this for some positive number a in any physically realistic situation. And so just thinking about what the characteristic equation is going to tell you, you're going to find that R is going to be purely imaginary, right? So something like this is an irreducible, you're going to get an irreducible quadratic, R squared plus A equals 0. And so you're going to get a purely imaginary answer. And so that's your indication that you're just going to get a pure sine and cosine coming out as your solution. So your complementary solution here is going to look something like C1 cosine phi t plus C2 sine phi t. And the frequency here, so phi, this is going to be the square root of k over m. And so this is called the intrinsic frequency, or natural frequency. And so in other words, this is going to be the frequency that your spring is bouncing around at if it's just left to its own devices. So you give it some initial conditions, like an initial slap, or you pull it back and let it go, something like that, and then you watch it bounce around. This is the frequency it'll bounce with. So now in the case when it's damped, okay, so now we've got C strictly positive, or your resistance R is strictly positive, either way. In this case, different things can happen. So there's 3 possibilities, and they all come basically from looking at that discriminant in the quadratic formula, and I'll talk a little bit more about what that means. So one case is that we get repeated real roots in our characteristic equation. So we'll end up with something that looks like this. So this is when we've got 2 distinct, oh, I said repeated, I'm sorry, distinct real roots. And then there's repeated real roots. Oops. So that's the case when it's repeated. And then we have the case of complex conjugate roots. And so in this case, psi is going to be our intrinsic frequency squared minus p squared in a square root. Okay, so these are the 3 different things that can happen depending on the values of your mass, coefficient of friction, and spring constant. And so the different situations that we have here come from looking at this discriminant right here. And so we say that the critical damping is it's going to be the square root of, or 4km. When c is equal to square root 4km, then when we plug it into this formula right here, it zeroes out the top and you get the repeated roots. So if you have, if you're in the case when c is strictly bigger than the critical value for damping, then this is called overdamped. And this is when you have two distinct real roots. When you have it equal, this is called critically damped. And these two actually look very similar. It's hard to tell the difference between them visually. Like if you're given a plot and somebody asks you, is this a critically or an underdamped system? They both look qualitatively very similar. So you can have something where it decays, or maybe decays like this, or it can even pass through equilibrium once, but only at most once. So you have some kind of solution that looks like that. As opposed to the underdamped case, so the underdamped case, and this is where we get the complex conjugates kicking out a sine and a cosine. And so for something like this, what you're going to have instead is you're going to end up with, well, we've got this exponential function multiplied by something sinusoidal. And so if you remember back to, like, I don't know, the second week or so, we saw that you can rewrite this linear combination of sine and cosine by introducing c1 squared plus c2 squared square rooted as the amplitude. We can rewrite this as ce to the minus pt cosine of, and then we've got phi t minus some lag like this. Okay, and so this part right here I would call the amplitude envelope. And so what I mean by that is that if you are going to graph what this function looks like, you would start with that amplitude envelope. So it's going to be some decaying exponential, so maybe, well, something like that. And it's going to be oscillating, so I'll also draw in the corresponding part on the negative side, something like this. And then if we look at the function itself, so this, or sorry, the oscillatory part right there, that's going to look like some cosine curve. And so there's going to be some delay. That's what the delta is telling us. And then there's also going to be some period here. So what is it? It's 2 pi over the frequency. And then the amplitude comes by being multiplied together. So when we multiply these two functions together, 0 times anything is still 0, so it's still going to have the same nodes as it did before. But now the amplitude will be modified by the blue one, so I just make it kiss the blue guy, and there we go. So this purple one right here is the resulting equation of motion. So we have that it passes through the equilibrium point infinitely many times. So some terms that come up when looking at things like this, we say that a solution or a function is transient if it goes away. All right, so transient means it moves away. And I'll just write down officially what I meant by amplitude envelope. So if you've got something that looks like CE to the minus PT cosine of something like that, then the amplitude envelope is CE to the minus PT, the thing that's multiplying the oscillatory part.